Hi, my name is Bahadur Ahmedov. Welcome back to the course of multivariable calculus. In this lecture, we're going to continue our discussions about the sequences. In the previous lectures, we defined a sequence as a list of numbers which are written in some order using a formula or some rule. We are going to denote a sequence in general as the A1, A2, and so on, AN, where AN is going to mean the nth term of a sequence. So we wrote a couple of examples of sequences. For example, every odd number can be written as a sequence, right? So it's going to be 1, 3, 5, 7, 9, and so on. And in a more compact form, we can write down the sequence of the odd numbers by introducing a general form of the odd numbers. So AN, the general form for the odd numbers, can be written as the ATN minus 1. And we can just put the curly brackets around this general formula and right here on the end it says n start from 1 until the infinity. So if you substitute n to be equal to the 1 to here, you're going to get 1. If n is equal to the 2, you're going to get the 3. If n is equal to the 3, you're going to get 5, 7, 9, and so on. And we also introduced so-called Fibonacci numbers in the previous lectures, where there is no such a general term for the Fibonacci sequence, but we can generate the n's Fibonacci numbers by just adding the previous t. So there is a recursive formula. Fn is going to be equal to the Fn minus 1 plus Fn minus t. The first two Fibonacci numbers start from 1, and in order to find the third one, we just need to add the previous t. It's going to be t. So in order to find the third one, we need to add the previous t. It's going to be 3, 5, 8, and so on. So here we are going to denote the Fibonacci numbers like this is the first one, the second one, third, fourth, fifth, sixth. And last time we've seen that actually so the Fibonacci numbers have been invented or have been used firstly in order to know the population growth of rabbits, where Fn would mean the number of rabbits in n's months. So if I would like to know, for example, hey, how many rabbits I'm gonna have after 12 months or 24 months, I just need to calculate Fn, or for example F12 or F24. So in general, for many other sequences, we would be interested to know how the nth term of a sequence is going to change, or what is the value of the nth term of a sequence where n is a huge number, so when n is big enough. So in this case, we would be interested to know whether the sequence is going to increase until the infinity, or whether the sequence is going to converge to some number. And in a moment, I'm going to explain you what do I mean when I say that the sequence is converging to some number. So let me explain you, let me give you an example of a sequence which is not going to converge. So example, which can be an example of natural numbers or even numbers. So let's say the even numbers are going to start from 2. So 2, 4, 6, 8, 10, 12, and so on. So in general, we can write down the AN, the general formula for this sequence, as a 2n, where n goes from 1 to the infinity. So what I would like to do is I would like to understand what is the value of the AN when n is big enough, when n goes to the infinity. For example, what's the value of the sequence when n is 1,000 or 1 million or 10 million and so on. So you can see from here that the sequence basically goes to the infinity, right? So as n goes to the infinity, the an is also going to infinity. So we say that the sequence doesn't converge, or we say that this sequence diverges. So now let me give you an example of a sequence which is going to converge. So let's consider Another example. So this is example from our previous lecture where we wrote down the general term of a sequence as n over n plus 1. So let me generate a couple of terms of the sequence in order to give you an impression what kind of sequence this is. So if n is equal to 1, it's going to be 1 over 2. If n is equal to 2, it's going to be 2 over 3. If n is equal to 3, it's going to be 3 over 4, 4 over 5, 5 over 6, and so on. So now, what I would like to do is, I would like to know whether if n goes to infinity, whether the sequence also goes to infinity, or it goes to some number. And in order to understand this, let me try to draw the values of the sequence. So here the y-axis is going to mean the values of the sequence, and this axis is going to mean the n, the values for the n, and this is going to be a n. So when n is equal to the 1, when n is equal to the 1, its value is equal to 1 over 2. So let's say 1 over 2 is here, or here. When n is equal to the 2, its value is 2 over 3, which is 0.66, right? So it's somewhere here probably. When n is equal to the 3, it's 0.75, so it's here. When n is equal to the 4, it's 0.8 or something like this, so it's going to be here. When it's 5, it's going to be here. When it's 6, it's going to be here. 7. Here, and so on. So basically, if I would just draw the values of an, I can see that as n increases, the values of the an are going to be really close to this value, which is equal to the 1. So this is 1, right? So as n is going to the infinity, the values of the an are going to closely to the 1. So we usually say that, hey, there is a limit, the sequence is converging as n goes to the infinity, and it converges to the 1. And this is important for us because it gives us some impressions how the sequence is going to change. So what happens with a sequence when n is increasing, when n goes to infinity. So here we've seen that the two different types of the sequences. One is called the diverging sequence. For example, when the values of the sequence is simply going to infinity, or they might go to the minus infinity, and the converging sequence, where the values of the sequence are getting closer to some value. So in general, we are going to write down a sequence or a converging sequence in this way. So let us write down the definition of the converging sequence. Definition. So we say that a sequence an has a limit L. It means that when we find the limit of the general term of the sequence when n goes to the infinity, it is going to be equal to the L. And if this exists, we say that the sequence is converging. Is converging or the sequence converges. So let's do a couple of examples how to find the limits of the sequences, or whether the sequences are going to converge or diverge. And in this case, we are going to do pretty much the same techniques as we did to find the limits of the functions. For example, so let's say find the limit of the sequence n goes to the n over n plus 1 when n goes to the infinity. So we can find its limits using the techniques which we used before. So we can just take out the n out of the brackets in the numerator and denominator. So it's going to be n. So if you take out the n in the denominator, it's going to be 1 plus 1 over n here. Right? So you can just cancel out the n's, and what you are going to have here is limit of n goes to the infinity, 1 divided to the 1 plus 1 over n, and we can find the limits of the numerator and denominator separately using the laws of the limits. So it's going to be the limit of 1 when n goes to the infinity divided to the limit of this term, 1 plus 1 over n, when n goes to the infinity. So the numerator goes to the 1, denominator goes also to the 1, since the limit of 1 over n is going to be equal to the 0 when n goes to the infinity. So the value of the limit is going to be simply equal to the 1. So we can find the limits of the sequences pretty much in the same way as we did before. So we can do another example here. Example number 2. Where we are given a sequence in this way, so n divided to the square root of 10 plus n. So if we need to find the limit of the sequence, we can do pretty much the same thing as we did before. So we can take out the n basically out of the brackets. So in this case, it's going to be a limit of n goes to the infinity. So if you would like to take the n here from the square root, what you need to do is basically you need to just take out, so divide everything inside the is square root to the n square. So it's going to be 10 divided to the n square plus n divided to the n square, right? So that whenever n goes inside to the square root, you're going to have pretty much the same term as in the beginning. So now we can just cancel out this n with this one, and what we're going to have here is the limit of n goes to the infinity of 1 over square root of 10 over n squared plus 1 over n. So whenever n goes to the infinity, this term goes to the 0, this term goes to the 0, so 1 over 0 is going to give you infinity. So we say that this sequence is going to diverge, or divergent sequence. So there are a couple of rules for this to find the limits of the sequences, which are very similar to the limits of the functions. Let me state a couple of them. So whenever you would like to find the limit of the two sequences, or the sum of the two sequences, or the subtraction, what you can do is you can just split them. So you can write down this as a limit of the first sequence when n goes to the infinity, plus minus the limit of the second sequence when n goes to the infinity. For example, if you're given a sequence like 2n, whenever you need to find the limit of the sequence, what you can do is you can simply split this into the two parts, like 1 over n plus limit of 1 over n. So of course you're not going to use this rule for this easy cases, but like we are going to use this for the more sophisticated cases. So this is the first rule. The second rule is the limit of the multiplication of the two sequences, an times bn, when n goes to the infinity, also can be found by finding the limits of the sequences separately and then multiply their limits when n goes to the infinity. And this works for many other rules, like whenever you are going to find the pairs of the sequences, like a limit of an in a pair of p is going to be equal as finding the limit of the sequence first of all, and then find its p's power, where p is going to be more than 0. And also, we've learned before about undetermined limits and so-called L'Hopital's rule, where we basically have a limit in a fraction form where the numerator and denominator goes to the infinity, and we can find this by taking the derivatives. So let's do an example of finding this kind of limits as well. So, example of a L'Hopital's rule. So let's say we are given the sequence in this form. So sequence is given in the form of ln of n divided to the n, and we need to find its limit when n goes to the infinity. So when n goes to the infinity. So if you basically put the infinity to here, it's going to be infinity, and if you put the infinity to here, it's also going to be infinity. So this is a limit in the form of infinity over infinity, which we call as a undetermined limit. Determinate limit, right? And we can find this by taking the derivatives of the numerator and denominator separately. So basically, the limit of ln of n divided to the n when n goes to the infinity, it's going to be the limit of the So the limit of n goes to the infinity. So we first of all need to take the derivative of the numerator with respect to the n in this case, and then divide us to the derivative of the denominator with respect to the n. So please note that we're not using the so-called quotient rule. We are taking the derivative of the numerator separately, then the derivative of the denominator. So they are taken separately. So we need to find the limit, n goes to the infinity. So the derivative of the numerator is going to be 1 over n, and the derivative of the denominator is simply going to be equal to the 1. So since the derivative of the n with respect to the n is simply going to be equal to the 1, so it's going to be the limit of n goes to the infinity of 1 over n, which is simply equal to the 0. So the derivative, or this sequence is also going to be convergent, and this is going to converge to 0. So as we increase the n, the values of the sequence are going to be closer and closer to the 0. So in this lecture we've learned, so let's make a summary. So in this lecture we've learned about the converging and diverging sequences. So sometimes, so let me draw this by the graph. So sometimes you might have a sequence which is going to converge to this number from the bottom or from the top, or sometimes you might have the sequence which is going to converge to this in this way, for example. So it's also like a converging sequence. So in this case, this is going to be L, this is the AN, this is the N. So as we increase the N, the values of the sequence are going to be really close to this value of L. So this is about the converging sequences. And we can find the converging sequences, or the limits of the sequences, by just finding the limits of the general term of the sequences, and we can use all the terms which we have, all the techniques which we have used in order to find the limits of the functions. And whenever we are talking about diverging sequences, it's a little bit more like more interesting, I would say. So, because for example, so sometimes you might have a sequence like n, or 2n, or 2n minus 1. An goes to 2n minus 1. As n is going to increase, the an is also increasing, so it's going to increase, for example, linearly in this case, right? So it's always going to increase, so it never converges to anything. But you might have more interesting cases as well, where so let's do this. An, for example, an is going to be given as the minus 1 in the power of n. So in this case, your sequence is basically is going to be whenever n is equal to the 1, so an is equal to the minus 1. Whenever n is equal to the 2, an is equal to the plus 1, n is equal to the 3, an is equal to the minus 1, then plus 1 and minus 1 again, and so on. So we can just put those values to here like this. Right? So if you just connect this, you're going to get this kind of like beautiful function which is also which is oscillating, right? So as you increase the n, it will never converge to some number. So it doesn't really go to the infinity or to the minus infinity, but it neither goes to some number. So it's really interesting sequence as well. So in this case, there is a theorem. So, but it also really depends on the an. So if this an is simply minus 1 in the power of n, then it's a diverging. But there was interesting cases where minus 1 in the power of 1 doesn't really make the sequence diverging. So sometimes they might converge as well. So in this case, in this sense, we are going to learn about this interesting theorem, which basically tells us that if there exists a limit of the absolute value of the an when n goes to the infinity, and this is equal to the 0, only 0, then the limit of an is also equal to the 0. So, which really doesn't work for our example here, right? So let's try to apply this to here. So in our example, an is equal to the minus 1 in the power of n. So what what I need to do is I need to find the absolute value of the an. So can you guess me what's going to be absolute value of an always? So it's always is equal to the 1, right? So the absolute value of the a1 is going to be equal to the 1, absolute value of the a2 is equal to the 1, absolute value of the a3 is equal to the 1. So it's always equal to the 1. So if you would like to find the limit of the absolute value when n goes to the infinity, since it really doesn't depend on n anymore, it's simply going to be equal to the 1. So what does the theorem tells us? That it doesn't matter whether it's going to reach infinity or some number, right? So unless it doesn't reach the 0, then the sequence is diverging. So basically it means that if this limit is not equal to the 0, then the sequence is diverging. If it is equal to the 0, if it would be equal to the 0, then so the sequence would be converging, and it would converge to the 0. So let me give you an example which shows this. So let's consider another example where the general term of a sequence is going to be written as the -1 in the power of n divided to the n. So now we can write down a couple of terms of the sequence in order to understand what type of the sequence is this. So it's going to be like when n is equal to the 1, it's going to be -1. When n is equal to the 2, it's going to be 1 over 2. N is equal to the 3, it's -1 over 3, 1 over 4, -1 over 5. Sorry. -1 over 5, and so on. So what we need to do is we first of all, so when you have this kind of sequence when the signs are changing from -1 to the +1, then to the -1, we are going to call those kind of sequences as alternating sequences. Alternating sequences. Alternating, because their signs are alternating, right? From minus to the plus, and from plus to the minus. So in this case, what we have to do first of all is we need to find the absolute value of the an. So if you find the absolute value, it's going to be 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, and so on. So they are the absolute values of the an, and here are just the ans, right? So you can see that when you find the absolute values of your sequence, you are going to simply have 1 over n, right? So if you find the limit of the absolute value of the an when n goes to infinity, it's simply going to be limit of 1 over n when n goes to infinity, which is simply going to be equal to 0. So now let's look to the theorem, and the theorem tells us that, hey, if it is equal to 0, then the sequence itself, the original sequence, is also converging to 0. So basically, -1 in the power of n divided to the n when n goes to the infinity is also equal to 0. It's converging, and it's converging to 0. So let's do a couple of more examples about finding the limits of the sequences. There is one more example which basically tells us that, hey, the limits can go inside to the function. So there was a rule. So let's find this. So let's find the limit of the sine of pi over n when n goes to the infinity. So the limits are so cool that they can even go inside the function, so they can just penetrate through the functions. So you can write down the limit of the sine of pi over n as sine of the limit of the pi over n when n goes to the infinity. So can you guess me? So whenever you divide a number to the infinity, a finite number to the infinity, so you are simply going to get the zeros, right? So its limit is equal to the 0. So it means that it's going to be sine of 0, which is equal to the 0. So this kind of sequence is also converging, and it's going to converge to the 0. So this is roughly what I wanted to explain to you in this lecture about converging and diverging sequences.